All right, so we are going to start today in chapter 1. Chapter 1 is really around math concepts that we use in chemistry. So maybe the harder component of the course, or one of the harder components, the organic component, is a little bit interesting as well and different from the math component. So we're going to start by looking at scientific notation, some of the units of measurement, and then making measurements in the lab and how we actually do this and why it's important. So scientific notation is often used in chemistry because we're often using very, very small numbers, right? If we're talking about atoms or something, they're very, very tiny and you have a lot of them present oftentimes. So scientific notation is very useful for being able to talk about numbers and do math with numbers that are very, very large or very, very small, depending on what you're doing. So scientific notation uses powers of 10. So for very large numbers, we could say 10 to the 0 equals 1. 10 to the 1 is 10 times 1, or 10. 10 times 10 is 100. 10 times 10 times 10 is 1,000. And then 4 tens, 10,000, 5 tens, 100,000, and so on. So our exponents then are just the number of tens that are being multiplied out in a row when we're thinking about scientific notation. Right? So for small numbers, we're going the opposite way, or doing division essentially with our exponents. So 10 to the minus 1 is going to be 0.1. 10 to the minus 2, 0.01, 10 to the minus 3, 0.001, and each number we're going to move back one more decimal place. So this is the basis then for scientific notation. So anytime we have a very, very large number, we need to first identify a coefficient that we're going to use with that number, and it will be between 1 and 10. So it will only have essentially one place, and then that's going to be multiplied by 10 raised to some cofactor or power. So that's the power you're going to need to multiply by to get it out to the extended number. So let's take an example. So if we have this very large number, right? I don't even know, million, billion, 579 billion. That's a lot, right? So this would be very hard to work with in the lab because it's a giant number and you'd be putting in a lot of zeros. Easy to make mistakes on a calculator if you're doing a math problem like that. You might miss 1 0 and then your answer will be off, right? So we need to first identify our coefficient. The coefficient is going to be all of the non-zero numbers. So in here, our coefficient is going to have to include the 5, the 7, and the 9, right? And so we find our coefficient, and we make it a decimal that has one coefficient in the ones position, and then everything else will be past that decimal. So for this one, that's going to be 5.79, right? And then step 2, we need to assess all the zeros that were past that in that number, right? So how many positions are there? That's going to determine our exponent for the 10 unit, right? So if we count from where our decimal place is, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 in this number. Right, so that is going to be our exponent number. And that's then how we write this. So 5.79 times 10 to the 11th. Right, we're essentially counting from where we put that decimal place in. Right, we don't need to show all the zeros anymore. They're going to be accounted for in the exponent position. All right. Okay, so with our very small numbers, it is a similar system. So this is a very small number, and again, you've got a lot of zeros in there. Punching that into the calculator, it becomes easy to make mistakes, missing zeros, right? So we want to write this guy in scientific notation. We first, again, find our coefficient. So that is all the non-zero numbers. And we're going to put 1 in the ones position, and then the rest of the number has to be past the decimal. So for this one, that is the 6.24 is going to be our coefficient. All right, step 2, we have to figure out what our exponent is going to be, right? So from wherever we're placing our decimal, we need to count all the positions from there. Right, so if we count back, we've got 1, 2, 3, 4, and 5 to that decimal. So that is going, when we're moving to the left, and it's a very small number, it has to have a negative associated with it for the exponent. So our exponent should be -5 for this one. And we would get an answer of 6.42 times 10 to the -5. All right, so now we have some practice. This is where we would use our Socrative, which I need to log in first. Lord. All right, so you can get into the Socratives either 2 ways. You can use the QR code, or you can use the name of the class, which is Chem 103 SPR2026. And you may need to download the Socrative app for the student version. Should be free. Yeah.
The student ID, is that our V number?
That is your V number, and it includes the V. So it'd be V00, whatever your number is. Yeah, that's your first quiz. What is your V number? Yep. And then hopefully I put it in right. So this is my test today too. But I see people are getting in. That's a good sign. You may talk to each other during the Socratives. Use a communal brain. All right, is everybody in? Yes, maybe? Everybody that's here today? All right. Everybody submitted an answer. All right. So let's go over this. So what would be the coefficient that we would need to make for this number? Yeah, so we need to use all the non-zero numbers, right? So it'd be 9.673. And then going backwards. Right, so that's going to be times 10, and we need to figure out the exponent. So I would start from where the decimal place exists in the real number, and then we're going to move it back to the position of right in front of the 9. Right, so we need to go 1, 2, 3, 4, 5, 6 places. So that is going to be our exponent for that number, or 6. So your answer here should have been the 6. Is that making sense? All right. All right, so this one is also asking for the exponent for this very small number, 0.000567. So what? And do we have all the responses? Best guesses? All right, very good. So what is the coefficient that we need for this number? Yeah, we need to include all of the non-zeros, right? So we need to have 5.67 would be our coefficient, right? And then the exponent, we are going to walk that decimal to the position right after the 5. So there's 4, and it was a very small number, so that has to be negative in there. So we've got a -4 for this number. All right. Let's see. No. All right, so this one is asking for the standard notation for this number. Times 10 to the 4th. It's always a test for me too. Like it's like show names, show answers. No, I wouldn't show any of those. So I'm glad I've got it set the right way. All right, we have all the answers. All right, so when we have a number that's written in scientific notation, we should be able to work the other way as well. So our exponent is going to tell us how many decimal places that we need to move. So remember, if the decimal or the exponent is positive, that means it's a very large number. So we're going to have to move the exponent out to make our number larger, right? So we start with our coefficient, right? And we know our exponent in this case is 4. So we're going to have to move the decimal place 4 times. 1, 2, 3, 4. And we're going to have to add the zeros in there, right? So our new position for the decimal place would be there, right? So this is 54,700 should be your answer. I think I heard some conversation about that out there. All right. And one more, whoops, oh, my hand, I must have copy pasted the hand. It's 8.3 times 10 to the minus 2. That was nice to you, not make you move it too far. All right. So when we're dealing with very small numbers, right, they're going to be designated by exponents that are negative. So that means we have to move our decimal to make the number smaller, right? So we're going to need to move it back 2 places. 1, 2. So we're going to need to add 1 0 and place the decimal place 2 places over. So 0.083 should be your answer there. Or you can add that 0 in front of the decimal place. I like to do that when I actually am writing out answers because a dot on your paper is sometimes hard to see. So this just clarifies that you mean to have a decimal place right there to add that extra 0 in front of the decimal place as well. So the difficult thing for calculations using scientific notation is in your calculator, you need to put a parentheses around that whole number when you're putting it into your calculator. So you need to start with the parentheses, put that number in, and end parentheses before you do anything with the number. Like say you were going to divide that number by 8 or something like that, right? If you had a problem that you were setting up. If you don't grab it and put it all in there, you'll just divide the 10 to the 6 by the 8, not the whole number. So you want to make sure you get the whole number in your process, whatever you're doing with that number. We'll get some practice doing that later in the term when you're calculating how many atoms are in a mole or something like that. All right. So that's scientific notation, and that's going to be really important for especially the beginning part of the class where we'll be talking about numbers of atoms and things like that. So in science, we use the International System of Units for our measurements. And this is kind of a global agreed upon system so that we can share information from one country to another. And it relies heavily on the metric system as well. So the metric system is super nice because it's based on units of 10. And 10 is pretty easy for us to conceptualize and use mathematically, versus the English system, which we still use in the United States, that is wonky and weird and uses 12s and hundreds and 44 and hectares and all kinds of weird things. So we'll stick with the metric system and then the other SI units for temperature and things in the class. All right. So for the metric system, this is our primary table that we'll use in the class. So for each unit, you have a base unit for that measure. And it could be a measure of mass, which would be the gram. It could be a measure of volume, which is going to be the liter. It could be a measure of distance, which is going to be the meter. And it could be a measure of number of molecules, or the mole. And so we'll get to what that means as well. Does anybody know how many atoms there are in a mole of something? Or molecules in a mole? Oh, I'm hearing Avogadro's number out there. Anybody remember it? Whoop. Oh my, go back. Yeah. Avogadro's number is 6.02 times 10 to the 23. That's how many things are in one mole. So that's a mole unit. It's a very big number, right? That would be like saying, you know how many things are in a dozen? That seems easy, right? 12? Get a dozen eggs? Well, if I asked you to go get a mole of eggs, you'd need to bring me back 6.02 times 10 to the 23rd of them, right? So it's a lot of things. It's useful when we're talking about atoms or molecules. So that'll be a number we come back to a lot. So you can have that base unit of anything, and then you can add these prefixes to the system. The metric system kind of uses these prefixes in the similar way that we use scientific notation, right? So that it's an easy way for us to show very big numbers or very small numbers by using a prefix. So the first couple, right, move by a factor of 10, 100, and then all of the units past that move by a factor of 1,000, right? So when we're going down from the base unit, this is where we're getting smaller units. And when we're moving up from the base unit, this is getting bigger, right? So this is moving by a factor of 10. And then all of these guys on up are by 1,000. Right, so when we get up to like giga and past that, tera, right, like these get into computer bytes, right, like, and then, what's past the terabyte? I don't know. So you're getting factors of 1,000 each time when you're going up, right? So a kilogram is 1,000 times the base unit, right? Or you have 1,000 grams in 1 kilogram. Right, so kilogram is the larger unit. The gram then is the smaller unit. But when you go down on this table, so say we had a milligram is 1/1000th of a gram. So it's a very small unit. Or there's 1,000 milligrams in 1 gram. So we can use this to talk about micrograms, nanograms, picograms, even femtograms. Right, that might be a useful term if we're talking about DNA. You may only need a femtogram of DNA, something so tiny you can't even see it, to do PCR and to do DNA fingerprinting and identify somebody. That's pretty cool. I mean, you're thinking you're leaving traces of yourself everywhere you go. So only need a little bit to get there. All right, so this is our metric system prefixes. Pretty much in the lab will be around maybe the milligram, maybe microgram or nanogram if we're doing any DNA or protein. And then kilogram, probably not. That's a big quantity for us in the lab. We probably won't be measuring out a kilo of anything. All right. So, but a gram, you might do that. All right. So, again, if we're converting between these two, we can use what we call conversion factors to help us convert between the two. So what this is saying, when you're going up, the kilogram is the bigger object. So what we're saying is the kilogram is 1,000 times the base unit, right? What that means is there's 1,000 grams equals 1 kilogram. So we can use that as a conversion factor. If we want to go from grams to kilograms, we can write this as 1 kilogram over 1,000 grams. That number is essentially 1, right? If we write it this way. So if we multiply any number by 1, it's just the same number, right? So if I had, let's say, maybe 2,500 grams of calcium, right? And I want to know how many kilograms that is, right? I can take that and multiply it by my conversion factor, right? My grams are going to cancel out, right? And then I will be left with kilograms of calcium. And if I divide by 1,000, I'm going to move my decimal place back 3 places. That will be 2.5 kilograms of calcium. All right, so we can use our table to convert between things, right? When we go down on the table, right, that's going to mean that we have 1,000 milligrams in 1 gram, right? And we could use that as our conversion factor as well. Okay. Oh, sorry, I wrote over that. But when we have a really small number, our conversion factor is going to be here, whatever that full unit is. And you can even go in between, like units. Each of these units is 1,000 smaller, right? So I would know there's 1,000 microliters in 1 milliliter, or 1,000 nanoliters in 1 microliter. It just jumps by 1,000 each time once you get past the centi. So the units, again, are by 10. And so we can just move decimal places oftentimes to get from one unit to the next. So it's a really useful measurement system when we're thinking about conversions, going in between them. Right? So if I've got these two, right, I can essentially cancel out 3 zeros from each of them, and then that's the unit between them. Right, so there would be, 1 million nanograms in 1 milligram. Like if we were looking that way to build another conversion factor. Okay. This kind of making sense? Using the table. It takes a little bit to get used to, but once you have it down, it makes it really easy to transfer in between the different units. All right. So if we're wanting to know how many nanograms are in 0.00005678 milligrams, we have to first identify what we have. We have milligrams, right? And we found this here. We have nanograms, and we know the units between them. So we have milligrams. We want nanograms. We need our conversion factor. We cross off the number of zeros between them. And then the smaller thing is the nanograms. It's farther down. It still has 6 zeros. Right. Nanograms equals 1 milligram. All right, so there's our conversion factor. And then we need to set up to do the math. Right, so we've got 0.1, 2, 3, 4, 5, 6, 7, 8. So this is not written in scientific notation. It's painful for me to even see the zeros. Make sure you've got the 4 there. Right, we've got milligrams. And then we need to set up our conversion factor. Do we want to put nanograms or milligrams on the top? Nanograms on the top? Yes, nanograms on the top because that's what we want, right? So we're going to want to put what we want on the top, what we need to get rid of on the bottom so that they can cancel out. So we're going to put 2, 3 nanograms on the top, 1 milligram on the bottom. Our milligrams then can cancel out, right? And we'll be left with nanograms. So anytime we're doing conversions, really important to write the units out so that you can cancel, right? That lets you know that you've set up your conversion factor the correct way. If you didn't, if you put the milligrams on top and the nanograms on the bottom, if you write out the units, you should catch it because the milligrams would then be squared. You'd have milligrams squared over nanograms, and that would look funny, and you'd be like, that's not right. I need to cancel out the milligrams and then try again. All right, so we need to move our decimal place 6 places. 1, 2, 3, 4, 5, 6. So our answer should be 56.78 nanograms for that conversion. That is a number that's much easier to deal with, right? I don't have all those zeros hanging out in front of it. So that's why the metric system is useful. We can just convert it to the unit that makes sense for us with whatever number that we have, right? So this would be much easier to put into my calculator, 56.78 nanograms. Questions? All right. Okay. And this just shows that work that we just did. And fortunately, we got the same answer. All right, let's let you guys do a little bit of practice. Okay. So this one is asking how many liters are in 3,263 milliliters. All right, so if we're looking at our table, I'm going to get those off of there, right? We need milliliters, right? Going back to our base unit. Right, so that is going to be 1,000-fold, right, for our conversion factor. This is essentially our 1 position. That's our base unit. All right, so how many milliliters are there in 1 liter? 1,000. All right, so that's going to be your conversion factor. So what do we have starting with? Right, we are starting with milliliters. We need to get to liters. Right, so my conversion factor, what needs to be on top? The liters, right? 1 liter over our 1,000 mils. Right, so this is dividing by 1,000. So I'm going to need to walk back my decimal place 3 zeros. Right? Or you can do it on your calculator and take 3,263 divided by 1,000. 0.263 liters. Is that a choice? All right. Everybody got the answer in. All right, so we've got 3.263 liters on this one. All right, you guys do this one. So, how many micrograms? All right, the symbol for micrograms is the mu symbol. I will often use a U on documents so it doesn't get changed back to an M like from the mu symbol, because that's a bad mistake. So R in 3,000 nanograms. Okay, these guys are next to each other in your table. So they are apart by 1,000-fold. Which one is smaller, micrograms or nanograms? Nanograms is smaller, so my conversion factor, right, has to be 1,000 nanograms in 1 microgram. All right, so see if you can set that conversion up. All right, do we have the final answers? Last chance. Best guess. All right. So here, again, we know we start with the 3,000 nanograms, so we can write that out. Okay. We want to get micrograms, so we're how many micrograms? So what needs to go on top? What we want. So we want the micrograms, so we need to have those on top. So we can put the micrograms on the top, the nanograms on the bottom. So we're going to divide the 3,000 by the 1,000 and walk our decimal place back those 3 places. 3 micrograms. All right. I think there's one more of these guys. Yep. All right. This is stepping farther back in the placement on the table. So how many grams are in 3,000 3,000 nanograms? Oh, stop. All right, so we're starting off with the same starting material, but now instead of getting it to micrograms, we want to get it back to grams. Is the number going to be big or small? Small. It's going to be small, right? Because a gram is way bigger than a nanogram is. So it's not going to be bigger than the number. So you can cross that guy off straight away. It's not going to be A. Right? It must be one of those other numbers. Well, you just did the conversion to micrograms in the last problem, and we said that was 3,000 nanograms equals 3 micrograms, so you can cross that answer off too. Now you've got it down to 2, and you need to evaluate C and D and see which one is the correct one there. All right, so to do that, maybe we should go back to our table. Right, so from nanograms back to the base unit, right, that's a lot of zeros. You have to keep them all, right? The base unit is 1, right? So we've got 1 billion in there, nanograms in 1 gram. That's our conversion factor. 2, 3, 4, 5, 6, 7, 8, 9 nanograms in 1 gram. That's a lot. A lot of nanograms. Nanograms are very small. All right, so we set up the problem then the same way, right? We're going to have what we start with, the 3,000 nanograms, right? Times our conversion factor. Which one goes on top? The grams, that's what we want. So 1 gram on top and all of those nanograms on the bottom. All right, that's a lot of places to walk back. We have 9 zeros, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where we need to put our decimal place. Is that a choice up there? Good. If we put that into scientific notation, what would that be? Good extension. Three times 10. 1, 2, 3, 4, 5, 6. And it has to be negative because it's a small number. And that's grams. Right? Or 0.12345 in standard notation. All right, so is this kind of making sense? Conversion factors, setting them up, what you want on the top, what you have on the bottom. All right. All right, so there's 7 major base units that we use in chemistry and some in physics as well. Our unit for length is the meter within the SI units. The main unit for mass you'll see is kilogram, even though we'll use the gram most often. Gram is the base unit in the metric system, but for the SI system they use kilogram because they're measuring things that are bigger a lot of the time in the SI system. Time is in seconds. Amount is in the mole. And we said for the amount, that was 6.02 times 10 to the 23rd whatever you're talking about. Atoms, molecules, compounds, pencils, cats, dogs. It's a lot. Yeah. Temperature is Kelvin for the SI units, but in the lab, we'll typically measure Celsius. So we'll see Celsius a lot in temperature as well. And we won't really play with electric current or luminosity. You can come to physics if you want to do those things. But it's the ampere and the candela for luminosity. All right. Okay, so the mole. We've already talked about the mole a little bit. It relates to Avogadro's number, right? And so 1 mole is 6.02 times 10 to the 23rd things. I will give you this conversion on an exam, but you'll probably remember that number till you die. Right? It'll be a number you see a lot in here, so you'll use it a lot. So just as 1 dozen thing is 12 things, 1 mole is that many of those things. So it's just a way that we can categorize a huge number of things. This number is also like super useful because it relates to the mass of compounds, which makes it really a brilliant discovery. And that has to do with how much a proton weighs and how much a neutron weighs, and we will talk about those things coming up in the future, the near future. But for now, we know a mole is 6.02 times 10 to the 23rd things, right? So we can do conversions between moles and numbers of things using that conversion factor of 1 mole equals 6.02 times 10 to the 23rd, right? So if we have an example of 5.32 moles of carbon atoms, how many carbon atoms do you actually have, right? So we know our conversion factor, right? 1 mole equals 6.02 times 10 to the 23rd carbon atoms. So that's our conversion factor. So this number, Avogadro's number, could be anything. For us, it's carbon atoms in this question, right? So you list out what you have. You've got 5.32 moles of carbon. Carbon is C on the periodic table. And what you want number of atoms, number of carbon atoms. Right? And what you know about the relationship, we create a conversion factor. So that conversion factor is right here. We know 1 mole equals Avogadro's number of things. And then we have to do the math. So if we start, we set this up just like any other conversion. 3.2 moles of carbon, right? And we want number of carbon atoms. So what has to go on top? What has to go on bottom? Carbon atoms on the top. So our big number, 6.02 times 10 to the 23rd carbon atoms up here over 1 mole. And again, your mole is going to cancel out of carbon atoms. Mole can be MOL. You can drop the E, or you can keep the E, up to you when you write it out. Right, so our moles will cancel. When you calculate this, practice this right now on your calculator, right? You want to keep this in parentheses. So I often start by putting in Avogadro's number first and then multiply it by 5.32. But you can do it either way, right? Just to make sure you get the right number when you're doing your calculations. Oop. Yeah. Oh, I wrote on top. Sorry. Here, but I did the problem at least down there. Okay. All right, so you should come up with 3.20 times 10 to the 24 on your calculator. Be sure you can do that calculation and come up with that answer on your calculator. For exams, you will not be able to use your phone on an exam because I can't tell what you're looking at. We have calculators you can use, or you can bring your own. I will bring those calculators to lab with me so that you can practice with them. You can stop by, check one out if you want. It's good to know how to use the calculator you're going to use on the test, right? So if you have your own, practice with your own. If you don't have one, let me know and you can practice with ours, right? So that you feel really comfortable when you get to the test and you're not like, oh my God, how do you use this thing? Because I don't want you to struggle with the calculator. I want you to, be working on the chemistry, not the technology. Yeah. All right, so we're setting up our conversion factors just the same way. What we have, what we want on the top, what we have on the bottom. All right. How about before we get to this one, we take a 5-minute break? Yeah. A little past the noon hour.
Is there any sign-up sheet that I should?
Nope. Yeah. As long as you're doing these guys or into the soccer kid. Yeah, that's perfect. I'll know you're here.
And then those count for participation and whatnot.
Correct. Yes.
Okay, great. Thank you.
Yeah.
So for the test, do you have to have the graphs memorized?
Oh, for the conversion factors?
Yeah.
I will let you know. I'll post what I give you on the exam
Okay.
so that you know exactly what you need to know and what you don't need to memorize.
So,
Yeah.
so will
Yes.
will those most likely be part of what we will be able to? Okay.
Yeah. So that you can use your table to make your conversion factor.
Okay. Thank you.
Yeah, I had a question about the resources for the first exam. I will make up your resource sheet and I'll get it posted at the end of this week so that you know exactly what you'll have in front of you on the exam.
What do you feel like in your sheet?
All right, a couple more Socrative questions. So this one, asking how many moles are in 8.91 times 10 to the 24 carbon atoms. All right, so what is our conversion factor again? Right, we need Avogadro's number again. 6.02 times 10 to the 23rd, in this case, carbon atoms. All right, so what are we starting with this time? So we're starting with carbon atoms. Yep, so we'll list what we have. All right, and what do we want to find? Moles. It's asking us how many moles, right? So which thing needs to be on top? Yep, what we want is moles. So we knew 1 mole over 6.02 times 10 to the 23rd carbon atoms in 1 mole. And that should give us our moles. So typically when you end up with number of atoms or number of molecules, that's going to be the really big number. If you're ending up with number of moles, that should be a much smaller number, like in the realm of 1 coefficient to maybe a 1 decimal place, something like that. So just as a check for yourself, if you're getting, 10 to the 23rd moles, you probably have your conversion factor backwards. Yep. You can also see the number that you have here, the exponent, is 24. Right? The exponent on Avogadro's number is 23. That's going to tell you have more than 1 mole, right? Because 24 is bigger than 23. So you can cross off at least one answer, right, straight away. One answer is below 1. So you can get rid of that one, right? Because you have at least 1 mole there. Does that make sense? All right, what do you guys get when you divide that? 1.48? 14.8? All right. I didn't calculate it. Oh, I'll let you guys finish. All right. But here again we see carbon atoms is going to cancel. When you put this into your calculator, be sure to put parentheses around that. Then hit your division sign. Put another parentheses and put Avogadro's number in. End parentheses equals. And it should give you the correct response. And do we have all the responses? Last chance. Last chance. All right. All right, so try putting that calculation in a couple times on your calculator. All right. This one, how many manganese atoms in 2.4 moles of manganese? All right, so our conversion factor, again, is going to be the same guy. 1 mole equals 6.02 times 10 to the 23rd. This time, manganese atoms. Okay, so this time we're given what? What are we starting with? 2.4 moles, right? Of manganese. So what do we want on top for our conversion factor? Avogadro's number, right? We need to find out how many atoms. In 1 mole of manganese. So our moles will cancel. And we should be left with atoms of manganese. So what would happen if you didn't have a calculator and you had to do this? No? It's not terrible. Ignore the 23 for a moment. You guys can do 2 times 6, right? 2 times 6 is how much? 12? Okay, so ballpark is going to be around 12 times 10 to the 23rd. We don't usually write scientific notation like that, though, right? We usually put the decimal place right after the 1, which would be a bigger number. So we'd have to bump up our exponent by 1, right? So it's got to be pretty close to 10 to the 24th. So you could find that without a calculator. Right? I didn't do anything with the 0.4, which is going to make it a little bigger. Right? I'm just like, oh, ballpark, it's got to be around 1.2 times 10 to the 24. Well, there's only one number up there that makes any sense. There's only one number to the 24th power. I'm sorry?
How can I go back to the Socrative? Because I
Oh, you went out? So it's always that name you can type in up here, CH103 SPR2026, or I can give you the QR code again. I won't change our room number for the entire term. The Socrative will always be CH103 SPR26. So our class in the term, spring 26. Yeah, and if you fall out of the Socrative, you can just jump back in and start answering again. I should be able to see all your posts. Very good. All right, let's go back to our lecture. Okay, so the temperature scale that is used by the SI units is Kelvin. That is the absolute temperature. So the absolute temperature, if you go down to the 0 in Kelvin, that's where everything stops moving, right? So molecules have inherent vibration to them or movement to them. But when you get to absolute 0, it's so cold they can't even move anymore. So that's our definition for absolute 0. That's not a state that we can really reach, absolute 0, but that's our definition. So in the Kelvin scale, water freezes at 273 degrees Kelvin, right? So that seems like, oh, that's a lot of Kelvin degrees. But that's just how far down absolute 0 is in the cold scale. Like it has to be really, really, really cold to get to absolute 0. And then it is equivalent once you get up into the degrees to Celsius degrees. So we can convert really easily between Kelvin and Celsius. We just have to add 273.15 to our Celsius degrees to get Kelvin, right? So it's almost a direct conversion between those two. That's very nice. The Celsius scale, we use that in the lab most of the time. So our thermometers, they'll read in both Fahrenheit and Celsius, but we use Celsius most often. Celsius is based on the phase changes of water. So we haven't talked about phases yet, but things can exist in 3 different phases. Does anybody know what those phases are? Solid, yep, liquid and gas, right? So you have solid phase, liquid phase, and gaseous phase, right? And your substances can move between those phases without changing their makeup, right? So water can exist in all 3 of those phases on the Earth. It's very unique. Not many substances exist in all 3 phases. But we can find areas on the planet where we have ice, right? And that's going to be the solid form of water up at the poles or down at the poles, right? We have liquid water, thank goodness. And then vapor as it gets hotter and your water vaporizes into the gaseous phase, right? And that happens at 0 degrees Celsius is the phase change between the solid and the liquid states of water. And then at 100 degrees, that's the second phase change of water, where it's going from the liquid to the gaseous phase. So Celsius is very nice, and it's based on the boiling point or the melting point of your water molecules, right? Fahrenheit is a little bit more crazy, right? So Fahrenheit is based on the coldest temperature somebody could make of a solution freezing a long time ago. That's kind of how random it was. So they put salt in water, and then they tried to freeze it, right? And so the 0 point Fahrenheit is that solution, right? Was essentially salt plus water, and that is like the freezing point. And that's the Fahrenheit scale. So 32 degrees Fahrenheit is the freezing point of just straight water, right, in the Fahrenheit scale. And then the Fahrenheit scale is not a one-to-one relationship with the Celsius scale. So the boiling point of water on the Fahrenheit scale is 212 degrees. That's where you start to see water boiling in the Fahrenheit scale. So the Fahrenheit scale is a little bit different. We still use it in the United States for most of our weather. We're in the Fahrenheit scale. In the scientific field, you'll see Celsius being used most often. But we can convert from all three of those. The Kelvin to Celsius, very straightforward. It's on a one-to-one conversion. The Fahrenheit to Celsius or Celsius to Fahrenheit, a little bit more difficult to calculate. I will give you these formulas. You just need to know how to plug in the numbers, right? So if I want to go to Fahrenheit and I have Celsius, I'm going to plug in my Celsius here, right? So if I had 72 degrees Celsius, I could figure out how much Fahrenheit that is by saying 9/5 times my degrees Celsius plus 32. Or if I have Fahrenheit, and I want to figure out what that is in Celsius, I can plug it in. I can subtract the 32 first, and then multiply it by 5, divide it by 9, and I'll get Celsius. So these are my conversions from Fahrenheit to Celsius. Once I have that, easy to go to Kelvin from there using my conversion for Celsius to Kelvin. All right. So if we say it's 98 degrees outside, we're going to mean Fahrenheit, right, when we say that. So if we subtract 32 from it, multiply it by 5, divide it by 9, we'll get 37 degrees, and that's Celsius. So this is body temperature, right? Normal human body temperature is 98.6. 37 degrees Celsius, also the same, right? Body temperature. All right. Oh no, we need our conversion factor. Right, so here's your conversion factor for the first question. Right, so what is the temperature in Fahrenheit, right, outside when it's 22 degrees Celsius? All right, so we're going to set this up the same way. When we want to find Fahrenheit, we're going to use this top equation.
This one my calculator came in, so I don't know if it's right. But it's on there. Do you believe it? Oh, you put on your. Yeah, I got it. Yeah. I feel useful. Yes. I think I can do that.
It's giving.
I mean, oh,
Yeah, it's already breaking.
we're having a movie night and shit.
Yeah.
Oh yeah.
I'm like, I need to watch that and wait. I've seen the Picture Perfect.
I watched that like 8 times.
Really? Really? I have not watched that.
And we have all the responses. Best guesses? All right. It's like my favorite temperature. All right. Whoa, this is a double conversion. All right, how many degrees Kelvin is 22 degrees Fahrenheit? All right, so we've got to go to Celsius first, and then from Celsius over to Kelvin.
So do I? Do I?
So do Celsius conversion first. So you're trying to find Celsius first. So do that. And then all you do is subtract 2 or that.
That's it, right? Like, and then I take what I got and then add.
You get a negative number, not
I think a negative number. Hell no.
All right, so remember your order of operations. Right, you got to subtract first.
You do Celsius. You don't find the Fahrenheit.
I already had you add.
We already had the Celsius.
No, we have to.
You don't find the Fahrenheit.
Oh,
Tricky.
Okay, wait, so what did you just give me this? This is my what? My Fahrenheit?
That's your
My
Celsius. Now add.
That's your answer. Okay.
Wonder Woman interview. Yarn. I feel really It's that one, right?
Yep.
You're all done.
Everybody else can kick that. Because I gotta kick that letter. Because I'm gonna re-put it in like every time I have.
Yeah, she said she'll go to the conversion. Yeah.
But she's gonna give us
And we have all the responses. Best guesses. Last chance. All right, so you should have gotten 267. All right. Okay, so this brings us to derived units. So we've been using kind of our base units now. For some things, we combine units together to get another unit or a measurement. So we've actually been talking a little bit about liters and our unit for volume. Volume is actually a derived unit, as well as energy, density, and drop factor. Drop factor is used often in medical situations where you're administering medication to a patient, say from an IV. You're watching the drops come out, and you got to figure out your drop rate to give them the correct amount of medication over time, right? So our first derived unit is volume. So volume is the space something takes up, right? And so we can think of a cube as having a volume, right? And so we can say 1 milliliter is actually equal to 1 centimeter cubed, right? So if we know our length, a centimeter is very small, maybe the size of my fingernail, right? And on 3 sides, if we have a little cube, that would be 1 milliliter. So our definition is actually 1 centimeter cubed is 1 milliliter. So that's a derived unit from our measurement, the length, the width times the height, right? On medical shows, they might be like, give me 1 cc stat, right? They're talking about 1 milliliter when they're talking about that. Yeah. So cubic centimeter, essentially, for that. All right. So energy is our ability to perform work. In the SI units, we use joules. In our English system, we use the calorie. This is also a derived unit. So you can see a derived unit of kilogram per times meter squared over second squared. So it's like how far can you move a heavy object in a second squared, right? Like that's your work, right, that you would have to do to put into that effort. So your measurement of work is the energy, right? And so our older unit of energy, the calorie, is still widely used. This is not the calorie that you see on your food labels. That is actually kilocalorie, but the food companies don't like to write kcal, so they just use the big C calorie for on your food labels. So for food labels, we have kilocalories or the big C calorie. Yeah, when you're thinking about that. Right, and so we can give like our food values as well for the work that it can do for us inside our body, right? Fat calories. For 1 gram of fat, it gives us 9 big calories per gram of fat. So fat has a lot of energy. For protein or carbohydrates, it's 4. Very good. Yes. So there's less energy inherent in protein and carbohydrates, but still very useful fuel sources and required for making all of our proteins and things inside the body. All right. So our big calorie, again, is 1 kilocalorie. And we know kilo is 1,000 times the base unit. So 1 kilocalorie is 1,000 little calories for our base unit. But don't feel bad about eating lots of little calories. Yeah. All right. And that's our conversions again for our major structural units that we take in as food sources. We're going to talk about these later in the term, about what these things are structurally inside the body, the carbohydrates, the proteins, and the lipids. All right, so density is another calculated value, and this is a physical property of all substances. It has specific density associated with it. So you can have the density of water, you can have the density of mercury, you can have the density of lead, and these are all different things. You can have the density of a feather, right? That's going to be very low density, might float, or a cork, right? Whether something you have is like lead is very heavy, right? It's a very dense object. You have a lot of mass in a very small volume, right? So density is mass over volume, right? So if you have a mass but it's distributed over a large volume, the density is going to be a lot less, right? But if you have a large mass and a very small volume, that's going to be a really heavy, dense object. So we'll do some calculations around density as well. All right, and then our drop units for medications. The drop factor is GTT per mil, and this is used to determine your drip rate, where the drops are the GTT, right? And so if we want to find a volume over time, we need our drop factor, which is the GTT per mil. Mils will cancel out, and we get a flow rate of GTTs per minute in this case. You could also do that per second, depending on what you're trying to measure. But minute is probably good in a medical setting, right? You can watch for a minute and see, oh, I got 14 drops. That's the drop rate I wanted. They're going to get that medication delivered in the right amount of time. Right. All right. I think I have to open a whole new activity. Maybe we will hold this practice until next time. And I will just close out for today. We only have about 5 minutes left. So things we've gone over today, we did a lot. We did scientific notation. We did our units of measurement, making measurements in the lab. We will continue to do precision and accuracy, rounding, and significant figures. So that's the rest of what we still need to get through in chapter 1. And that would start with precision and accuracy. Let's just finish this out and then I'll let you go. All right, so precision and accuracy really talks about how you measure things inside the lab. And so these are two different terms, right? Precision usually is going to be referring to you, but you can affect the accuracy of your measurements as well. But it's how well do you make those measurements in the lab, and that's going to be a repeatability. Like if you repeat the experiment 3 or 4 times, can you get the same measurement every time? Right? So it's how careful are you? Are you walking to the balance and then you spill some on the floor and you don't care, and then the next time you don't? Like your precision is going to be off, right? And it'll be like all over the place, right? So this first one is inaccurate and imprecise. Oftentimes the instrumentation that you're using has to be calibrated using standards to make it accurate, right? So if you're weighing stuff on a balance, you want it to be zeroed correctly, and that if you weigh a kilogram measuring tool, that it actually measures a kilogram, right? You don't want it to be off, right? So you have to make sure that your balance is working correctly before you use it. That's going to get to the accuracy of that instrumentation. So if you are inaccurate, but you're precise, right? So say my balance is not calibrated correctly and it's off, and every time I'm measuring a kilogram, I'm actually measuring 1.1 kilogram. Doesn't matter how many times I do it, I'm still not going to be on the bullseye. But hopefully I'm clustered in one area and my tool use is good and I'm repeatable in your measurements. So that's precision, but inaccurate. When you have both, right, you're making good measurements in the lab and your instrumentation is calibrated correctly, you will have accuracy and precision both in there. All right, let's save rounding for the next time. That's a bigger topic, and we'll have more questions. All right, good first class. See you guys on Wednesday.
2 questions for you.